The purpose of this first lecture is to give you a review on the materials that will be included on part 2 or on test 2. In part 1 of these videos, I'm just going to go over the topics that are covered on test 2 with some materials that are directly from your textbook. So what we did in the class, just going over topics in general, we started this section talking about special functions. There were two types of special functions that we went over. We went over step functions and how to represent windowed functions, switches, pulses, etc. using step functions. Then we went over impulse functions, and one of the key things for the impulse function was the sifting property. In other words, how do impulse functions behave under integration with other functions. The second topic then was the Laplace transform. We went through the Laplace transform definition and how one finds a transform through integration. And then we also went through how to use the tables and properties of transforms in finding the Laplace transform of functions that may or may not be in a table. The inverse Laplace transform was the next thing we looked at. We looked at how to use the tables. And then we looked at partial fraction expansion techniques. We talked about rational functions in the Laplace domain, how we have a polynomial in S in the numerator and a polynomial in S in the denominator. And if it's a rational function and we take a partial fraction expansion of it, remember that the numerator will have to be of lower order than the denominator. We said that we talked about poles and zeros, how they behave in the time domain. We went over the initial and final value theorem. We went over equivalent impedances and circuits and sources in circuits in the Laplace domain. And then we looked at how to replace circuits with their Laplace equivalent. So these are the topics that will be covered on exam 2. So just looking at some chapter summaries from your textbook with relevant page number links. The Laplace transform is basically the definition of the Laplace transform is given in this equation. It basically takes an expression in the time domain and through this transforming integral converts it to an expression in the S domain. And remember, S is a complex frequency, sigma plus j omega. The step function was the first special function that we described. It basically experiences a discontinuity from one constant level to another. Typically that is 0 to 1. That's referred to as the unit step. If we have some number other than k, then the step function takes on an amplitude greater than 1. If instead of u of t we have u of t minus some time shift, then that step discontinuity occurs somewhere other than 0. Otherwise, if it's u of t, then the function goes from 0 for t less than 0 to 1 for t greater than 0. The impulse function is defined through the integral. Basically, the impulse function is 0 everywhere that t does not equal 0, and then the impulse function has infinite amplitude at t equals 0. Your textbook defines a functional transform as the Laplace transform of a special function. Important functional transform pairs can be found in table 12.1, and then your textbook author has a second table that he refers to as operational transforms, which go over mathematical properties of the Laplace transform. These are summarized in table 2. Many authors and tables will combine tables 12.1 and 12.2 into a single table. The mathematical properties of the Laplace transform, this would be things like the derivative property, the time shift property, the property under multiplication by e to the 8 minus at, and so on. In lump parameter circuits, f of s is a rational function of s, and you can find that definition in your textbook on page 442. If it is a rational function, in other words, if it's a polynomial in s in the numerator and denominator, with the order of the numerator being lower than the denominator, then you can find its solution. You can basically take an inverse transform by doing a partial fraction expansion. If it's an inverse rational function, then basically you inverse transform, or if it's an improper rational function, you inverse transform that first by expanding it into a sum of polynomials that would include a polynomial plus a proper rational function. In other words, you divide the denominator into the numerator in order to be sure that in your fractional term you have a rational function. So f of s can be expressed as the ratio of two factored polynomials, so your numerator polynomial and your denominator polynomial. The roots of the denominator are called poles, and if we were to illustrate a complex plane, those poles would be plotted as x's, and the roots of the numerator are referred to as zeros. Those are plotted as 0 on a complex plane, and you can see an example of this on page 452. So f of s then is your function in the Laplace domain. The poles are the roots of the denominator, and the zeros are the roots of the numerator. The poles can be used to determine how the function behaves in the time domain. We'll talk about this a little more at length when we go over some examples and look at some actual functions. Finally, the final value theorem says that we can determine the final value of a function in the time domain if we take f of s, its Laplace domain expression, multiply it by s, and take the limit as s goes to 0. So this is valid as long as all of the poles, unless you have a pole at the origin, in other words, unless you have a 1 over s term, that all of the poles lie in the left-hand side of the s-plane. So there are some functions to which you cannot apply the final value theorem. These typically would be functions that have poles in the right-hand side of the plane. Those would be poles that have positive exponential growth, and so they basically would have an undefined final value. The initial and final value theorems allow us to predict the initial and final values of f of t from an S-domain expression. So in your textbook on page 453 is a detailed discussion and definition of initial and final value theorems. Now we also talked a little bit about the use of Laplace in circuits. We did not get very far into chapter 13, so the material that will be covered on this exam will be strictly limited to the discussion of what's in the next couple of slides. So the first thing we talked about is how circuit elements in the S-domain can be represented by taking the Laplace transform of the voltage-current relationship. So a resistor can be, the voltage-current relationship can be written as just simply V as IR. An inductor, the voltage-current relationship comes from the derivative property and can be written as follows, where I sub 0 is the initial current through the inductor. Capital I and capital V would be the voltage and current in the Laplace domain. And then the capacitor relationship can be written as follows, based on application of the integral property. So given this, you can come up with an equivalent circuit expression. Here for the inductor, this looks like 2 voltages in series. Here for the capacitor, this looks like 2 voltages in series as well. And so when we look at our summary of S-domain circuits table, a resistor in the time domain can be replaced with a resistor in the Laplace domain. An inductor in the time domain can be replaced with an inductor in series with a voltage source, which is more commonly written as an inductor in parallel with a current source. So this is typically the replacement that you will make for an inductor in the Laplace domain. And the capacitor is typically represented as a capacitor in series with a voltage source. As we discussed in class, the Laplace current is the current, obviously, through the series equivalent. So if you have an inductor, it's important if you're solving and you want to go back to the time domain to get your current, it's important to solve for the current into this node, because note the current will divide So if you only find one of these currents in your circuit, you haven't actually found the current that was in the original inductor. The same is true for the capacitor. The capacitor voltage is defined as the voltage from node A to node B. So if in your Laplace equivalent circuit you only find the voltage across the equivalent capacitor and you don't include the equivalent source that contains the initial condition, that will not be the same voltage. So in order to solve for the capacitor voltage, you will have to find the voltage drop from node A to node B in the Laplace domain and then convert that back to the time domain. So that's occasionally a source of confusion for students. I think it's important for me to point out. On this exam, you're not actually going to be solving for any currents or voltages. I just want you to know how to make these replacements in a circuit to find an equivalent circuit. So that'll be discussed next time. So that's the end of the summary that talks about topics, as well as giving you references to areas in the textbook that you can look at. The next part of this review, I want to show some specific examples as well as some of the solutions from the back of your textbook. So we'll do that as a separate video so that we can keep these videos short.